I'm going to call Jerry Mitrovica up here. Jerry, we're going to have to accelerate your appearance. The headline reads, "Sea level rise around North America upon collapse of Arctic ice sheet to be higher than expected." People thought only maybe 5 meters, but turns out maybe 6 or more. The source of that is CFAR scholar Jerry Mitrovica. Tell us what you've been up to. Thank you.
I've realized that scientists use a podium as a security blanket. So I'm not going to have my security blanket with me today. And I hope you don't mind, and I hope Moses doesn't mind, but I'm going to give this talk in honor of my quite ailing 84-year-old mother. She raised 7 children as a young widow in a very difficult time, both in Australia and in Canada. She taught us, the theme of my talk is going to be unconventional ideas. And if somebody taught me about unconventional ideas, somewhat crazy ideas sometimes, it was my mother. And she also gave her children one piece of advice that I give my graduate students, and that is that you don't worry too much about what people think. That's the best advice I think I can ever give my graduate students, and that's advice my mother gave me. I'd also like to acknowledge, I don't have a thing, acknowledge CFAR, the Canadian Institute for Advanced Research. This is really the jewel in Canadian science. If you don't know about CFAR, you should find out about it. It cultivates unconventional thinking. There's that word again. It funds me, it funds a lot of international scientists. We get together, we interact. The amazing thing about them is that I go to them and say, well, I'm sort of sheepish because I have some sort of crazy crackpot idea, and I go to them, and what I typically hear back in one way or the other is, well, that's okay, we'll fund you anyway. And that's the sort of response that any scientist wants to hear from a funding organization. Well, as I said, I come from a big family. I have a brother who is a journalist, very well-known Canadian journalist, another brother who runs a nonprofit. I have sisters who are social workers, educators, entrepreneurs. We have an entrepreneur. So in that sense, I'm the genetic aberration. I'm the only scientist anywhere near my family. And I think being raised in that environment gave me a sense, even though I was strongly supported in my endeavors, scientific work, that the public thinks of artistic creativity as distinct from scientific creativity. They really do. And in every venue I attend, I typically get that sense reinforced. And I don't think that's true. I lived in New York at one time, and I became a great fan of the American artist Mark Rothko. And I don't think Rothko's creativity stemmed from some sort of mysterious well. I just don't believe it. He was trained in the fundamentals of his craft, line, perspective, and he asked innovative questions, in his case about color, right? Why is it that when you put 2 colors together, the synergy makes so much stronger impact on the observer? And what if you blur the line between those 2 colors, does the observer become restless in looking at that artwork? If you haven't seen Rothko, you should, and I bet that that's what you'll feel when you look at his amazing abstractions. In the same way, scientists also deal with fundamentals. I may be the only person on Earth who admits to liking both Rothko and Newton, right? But I do, and I understand that Newton, in some senses, provided us fundamentals, and the important thing for scientists is to move beyond them, to ask the same innovative questions that Rothko's are asking in an artistic environment. We have to ask them in the scientific environment. There's no doubt that there are differences between the artistic and scientific endeavors. That's for sure. I was at a conference just last week in Berkeley, right on the St. Andreas Fault, so scientists are a reckless bunch. And in that conference, I brought up the issue. I was going to give a talk at a conference on ideas, and somebody pointed out the novelist C.P. Snow. Snow apparently wrote about the differences between the artistic and scientific sensibility. He said there is a known world and there's an unknown world, and there's this middle ground of ambiguity. And scientists really try to wrench every last ounce of ambiguity out of that middle ground. That's what our purpose is, to move that line a little bit. Yes. Artists don't do that. They revel in that ambiguity. They elevate it. They cultivate it in some senses. They certainly use it to reflect the human condition. Just as Fitzgerald said, he said, vagueness in great artistry causes deep interior laughs. And in a sense, good science causes you to stop and think more deeply about what's going on. But the fundamental question, or the fundamental issue, is asking innovative questions. Moving, if you will, in a cliched sense, outside the box, right? That's the cliche. I was talking at a break earlier. I told an amusing story about a student I met who thought outside the box. I was a judge at a science fair just a few blocks away from here, and my role, which I dreaded, was to shepherd 10 grade 3 students in. They were going to tell me about their projects. The first thing I noticed that there is no way on earth that they could have built what they had in their science fair. Their mother or father was definitely a PhD in engineering. So I ranked as number 1 this little cocky, self-assured kid named Joey who had built his own sundial, cut it out of cardboard. It was terrible. But I was guaranteed that Joey had done it himself. And I brought Joey to the rest of the judges, and I asked Joey some questions. I said, for example, can you use this 24 hours a day, Joey? And Joey said, no, can't use it at night. I said, good, good. And can you use it every day, Joey? And he said, yes, you can. I said, really? Every day? Even on a cloudy, dark day? And he goes, then he looked at me like I was a moron. He said, no, it's made out of cardboard. The rain will ruin it. Right? So, that's thinking outside the box. I keep track of him because I'm hoping he'll go to graduate school. And maybe I'll meet up with Joey again. If you're anywhere in the audience, Joey, call me. But now let's move from Joey to a much more eloquent expression of what it takes to be creative. I'm sorry for this somewhat labored introduction. And that's from Walt Whitman, another person I'm a great fan of, this great rebellious man of letters in the 19th century in the US. Talk about a rebel. In his Songs of the Open Road, he wrote this: "From this hour I ordain myself loosed of limits and imaginary lines." I give this quote to all of my graduate students. I tell them, understand the fundamentals, read the textbook, internalize it, then forget it. Listen to these great legends in your field, internalize what they have to say, and forget it, right? And eventually you'll also forget me. You'll leave me behind. That's the point of training graduate students. Move forward, and I tell them to keep this at heart. And the most important thing, perhaps, isn't what Whitman said. The most important thing is what my mother said. Because when you do this, it's important to not care too much what people think. That's the best advice you can give a scientist, particularly in climate change research, where everything you write about is scrutinized so much. So what I'm going to try to do is try to give you a sense of how that philosophy of thinking about things a little bit differently, of not caring about the boundaries of the field, has helped us to resolve two very fundamental enigmas in climate research, and in particularly in sea level research, the research that I'm involved in. If you go back, the main thing, all of the speakers in this 3-day meeting want to entertain you, but I'm sure they all want to educate you. And what I want to do is, in 15 minutes, I want you to be able to go to a conference on sea level change. And when you hear somebody get up and deny that global change is happening on the basis of sea level research, you can look them in the eye and say, that simply is not true. Right? So let's see if I reach my goal. If you go back even a few years in global change research, sea level research had two enigmas related to it. The first was that sea level seems to, I guess it's a laser pointer, right? Sea level, which is going in and out. I don't really need it. Sea level research, sea level seems to vary strongly from place to place. If you go to St. John's, if you go to Miami, Australia, etc., all of those areas measure sea level change that is different from one another. And that defies simple logic. The idea is if the ice sheets are melting, sea level should be rising more or less uniformly. So what is the problem? This was number one on sort of a Dave Letterman top 10 list of why you shouldn't believe climate change is happening. The second is, and this is something I hear even today, people will come up and say, yes, we accept that sea level's rising 2 or 4 millimeters per year now, on average globally. But that's been happening for thousands of years. You've probably heard that, right? That's a lie. And I'll show you why that's not true. Okay? So let's start with the first one. Here I've just taken an image from, I really do need a pointer, so I hope this will work. Yeah, it sort of comes in and out. So I take an image here off the web of a tide gauge site. Tide gauges are very low-tech installations. We certainly use satellite data for this kind of work now, but I wanted to describe to you this special data set where we have 200 years of data. These are simple cylinders with a ping pong ball inside. It's a little bit more sophisticated than that. As water goes up and down, this float goes up and down, and you just need some way of measuring that year after year, decade after decade, century after century. And this is an example at bottom left here of a tide gauge installation in northern England. That's pointing to some satellite feed right there. I guess I can't see it. I think that's just a toilet, so I don't know. I was trying to come up with something impressive, but I don't know what that is. And so each one of the black boxes there represents a tide gauge site. At that location, well away generally from large cities, where because we pump groundwater out, cities are subsiding. We want to stay away from that kind of contamination. We want to stay away from tectonic contaminations. If you look at those 24 sites, now let's ask ourselves, what are the sea level trends in the 20th century that you get at that widely distributed network of sites? On the right, the y-axis here is sea level rate in millimeters, and these sites here, like Newell and Brest, the first few are in Europe, then we've got New Zealand, the west coast of the United States, South America, and the east coast. They're not really grouped in any significant way. All I want you to look at is, yeah, they vary. Some's half a millimeter, some 3 millimeters. It's all over the place. And so if you don't know any better, you can do one of two things. One, you can say, can't be global climate change. Ice sheets are not melting. The second thing you could do is take the average, that's what that red dotted line is, and publish a paper and not know what all that variation is about. In fact, that average is so well placed in the literature that those first 6 or 7 sites are European sites. They show sea level rates lower than the average, and that has a name in this literature. It's called the European problem, right? Why is it that Europe sea level is going up slower than it is everywhere else on the globe? But if you think about that even for a minute, if you stop thinking about the textbook and you're this bright young graduate student says, why should they go up uniformly? You ask that question instead of listening to people over and over tell you why. On the left, that's what you're assuming. If I take my ice sheet and I melt it, sea level rises uniformly. This is what we now call the bathtub model. That's what you're thinking when you think that it should go up evenly. But water doesn't behave that way, right? In fact, I've worked for 20 years in sea level research off and on, and I'm about to show you the most counterintuitive result of my career. And that is, this is what happens. Let me try to explain. An ice sheet is massive. It's like the sun and the moon. Of course, it's not that massive. It pulls on the water. It produces a tide, just like the sun and moon produce ocean tides. You have a large ice sheet, the water will be piled up towards it because of that gravitational attraction, Newton, right? If the ice sheet melts, two things happen. One is you certainly throw water into the ocean. You're not getting around that. But the second thing is you relax the tide. It doesn't hold on to the water as much as you think it should. That's incredible, because that means that close to the ice sheet, you see where this blue line falls under the dashed line. Sea level actually falls. If you're standing next to the Antarctic ice sheet and I tell you tomorrow that ice sheet's going to catastrophically collapse, right? Sea level will fall 150 meters at your feet. But you pay the price somewhere, right? The further you get away from the ice sheet, the higher is the sea level rise. This is now known as a fingerprint. Let me give you a specific example of a numerical model. This is a computer simulation of what would happen if the Greenland ice sheet stuck there in that, I don't know what color you'd call that, teal. My designer friends would be puking now if they saw my choice of color for the ice sheet. If that ice sheet melts, turquoise, somebody said. It's not teal, I guess, right? What we've done is a simulation where we melt the ice sheet and we allow sea level, enough ice that water, if it was the bathtub, would go up exactly 1 meter, right? From my foot to my hand. But then we say, what actually happens when that happens? Well, what you see, again, this pointer is finicky, but what you see is that sea level actually falls in this deep blue area, and it rises more and more. You better not have property in Tierra del Fuego. Sea level falls in this band. If the Greenland ice sheet melts, sea level will fall in Newfoundland. If you have a friend They shouldn't be concerned except in some general humanistic sense that the Greenland ice sheet has collapsed. Sea level is going to fall at their feet. It's going to increase by 30 or 40% more than this bathtub model in southern South America, all because of this tidal effect. There are other second-order effects in here, but that is pretty dramatic. Water falls within your feet. When an ice sheet melts, the sea level change is highly non-uniform. And every ice sheet has a distinct geometry of sea level change. The Antarctic, Greenland, all of them, so we call them fingerprints. So if you're around looking at these tide gauge sites again and you see all this variation, instead of throwing it out, calling it the European problem, taking the average, you're a graduate student who says, wait a minute, that variation is telling me much more than the average sea level rise. It's telling me where it's coming from. And in fact, the European data, if you followed my logic, this European problem here, that's easily explained. All that means is that Greenland in the 20th century has been melting significantly. Europe is close to Greenland. The sea level rise you see there will be less than everywhere else. It's easy to explain this variation. If somebody tells you now in the future that that variation proves that global climate change is happening, then you would say, that is simply not so. That variation is telling us now, we're using satellite data to do this, is telling us not simply the average, but where it's coming from. We measure Antarctic melt this way, Greenland melt this way, Alaskan melt, the Alaskan ice sheets are popping off very quickly. We see the sea level fall using satellites around Alaska from this gravitational effect. So let me now talk about this second point. Is this sea level rise unusual? And I'll show you very quickly a series of ways in which we show that it is not unusual. Well, for scientists, it's not unusual, but it certainly has not extended past the last 100 years, right? Only in the last 100 years. How do we know this? Here's one good example. I was born in Australia, Melbourne, left when I was very young. These coral reefs, these exposed coral reefs, are endemic to the equatorial Pacific. You see them everywhere. What they show is that in the last 3,000 or 4,000 years, because the top of that coral was alive 4,000 years ago, sea level has actually fallen a couple of meters. Now, if sea level today is rising 3 millimeters per year, if you go back 4,000 or 5,000 years, and that was not unusual, that was happening not only for the last 100 years, but the last 5,000 years, this would be under 10 meters of water, right? It would not be exposed this way, right? One day it will be exposed because levels are rising now, right? But 5,000 years of what we're seeing today would be 15 meters of water. It ain't so. Let me show you another example of an ingenious study that was just published by a close colleague of mine, Kurt Lambeck. Kurt and I were discussing in the Mediterranean the idea of how we might show, other than these corals, whether there was another way of showing how much sea level had changed in the last 2,000 to 3,000 years. And Kurt had an incredible idea, having a training in archaeology. He said, Roman fish tanks. It turns out that the Romans fish farmed. They caught their fish, they put them in holding tanks. And so these aren't the most glamorous of archaeological ruins. People don't care about them now, right? But they're very interesting because the Romans stuck their fish there. When they were ready to eat them, they took them out. But as you can imagine, the top of those tanks could not be more than a certain height above or below high tide. If they were, the fish would get out, right? So these were very accurately calibrated to be about 4 inches, right, below the high tide height. So what Kurt did is he went to all of these sites and he looked at these piscine, as they're called. This was a diagram adapted from a Roman diagram, where there was a sluice gate, etc., to keep fresh thing. Here's the tanks. There's Kurt standing there. I had to give him credit, right? Look at them. They're only a few millimeters, well, actually 4 inches, sorry to use that unit, plus a few millimeters more under sea level. If sea level had been changing 3 millimeters per year for 2,000 years, these would be under 6 meters of water. It isn't so. What we're seeing today is highly unusual. So now I want to end with an example that's a little bit more subtle that my group is involved in particular a great graduate student. I'm going to give you a little quick tutorial on rotation. The Earth rotates around its axis once a day. That's 86,400 seconds. We like to think of this as a perfect timekeeper, but that isn't so. The Earth's rotation rate changes all the time for a variety of different reasons. And how do we know what rotation's been doing in the last few thousand years? We look at ancient eclipse records. So what my group and I do is we go to Babylonian, Chinese, Arab, and Greek lunar eclipse records. We have a lot of help. We're not the archaeologists. I shouldn't take credit where it isn't really true. And each of those measures the occurrence of an eclipse. They were astrologers, and I think there's somebody talking on this later today. They were worried, right? Because eclipses were omens of bad tidings. They weren't astronomers in our modern sense. But they very accurately measured the timing of these eclipses. If we take when those eclipses occurred, the tablet there is a Babylonian clay tablet, and I don't read Babylonian, so I can't tell you what it says, but it's recording a lunar eclipse. If we take when the Babylonians said it occurred, and it occurred when they said that it occurred, the errors are only minutes, right? And then we say, well, wait a minute, when would that eclipse have occurred if the present-day rotation of the Earth, 86,400 seconds, had stayed constant for thousands of years, right? When we do that, we find out that this Earth of ours is slowing, right? It's slowing enough so that, sorry, I keep pressing this as if it's a pointer, that y-axis there adds up to 16,000 seconds, 4 hours. In 2,500 years, the record of when the Babylonians said an eclipse occurred to when we would predict differ by 4 hours. In other words, if we had two clocks that were synchronized right at that moment, right, one that was stuck on the Earth and one that was just exactly today's rotation rate, they would come out of phase 4 hours. And it's a very gentle descent. The Earth is slowed by about, now we know, 12 millionths of a second per year, right? This is hundreds of times the observational error. So this is known. It's very tiny, but it adds up over 2,500 years to 4 hours. The Earth is slowed because it's slowed, the period of the rotation has increased by 12 millionths of a second. Well, now, what about today? So that's what's been happening the last 3,000 years. What about today, the last 10 years, when we think global climate change has happened? Well, when we look at that, we see, using satellites, we have very accurate measurements of what's happened. It turns out the Earth has slowed more than the average. 15 millionths of a second per year has its rotation rate increased. I know this is subtle, but what we're really saying is recently, when we think global climate change has occurred, the Earth has slowed more than it's been slowing over the last few thousand years that we look at when we see eclipse records. Why is that? Well, that's because the ice sheets are melting. If ice sheets melt as they are today, water goes from the poles to the equator. Think of the figure skater. You put water at the equator, you slow it down. And that 3 millionths of a second per year is about 1.5 millimeters of global sea level rise. Exactly what we saw in the 20th century. So if I could just have 1 minute, I have two overheads. The Antarctic Ice Sheet, Moses alluded to this paper that we wrote that came out a few months ago that argued if that ice sheet goes, and we're particularly concerned if it goes, we're in trouble. Why is it that we're concerned if it goes? Well, it's because the western part of the Antarctic, this area here, there's enough water there that if we spread it over the oceans, we'd get about 4.5 to 5 meters of sea level rise. That region, the West Antarctic, is under sea level. It's sitting on bedrock that would be ocean if the ice sheet wasn't there. And that's really scary, because if an ice sheet pops up off its bedrock and gets broken up, it can go very quickly. So what we did is we published a paper, I'm just giving you this one slide of it, that showed, because of these tidal effects and because of other effects that I don't have time to describe, if the West Antarctic ice sheet does pop off, it's not going to be 4.5 meters over North America. We get a triple whammy of effects. It's going to be closer to 7 meters over North America. So is that our future? Well, that's my future, right? These are my two nieces, and I had hair then. The niece on the left, Aurelie, is now at the London School of Economics doing a PhD. It's hard to believe. The one in the middle is a publicist, right, of all sorts of weird European rock bands. They live in Europe, and neither of them went into science, even though I tried and tried and tried. I'm the godfather for both of them. You don't know how much time I spent with them teaching them statistics, right? Right? But despite my efforts, it wasn't exciting for them. Go figure, right? And they aren't scientists, right? But I do worry about them. And even though they're not scientists, I think, even though I've not made them a scientist, I've given them an appreciation for science. I've given them the ability to get up at those meetings that they have every week in Europe and say, that isn't so. Global change is happening, and sea level proves it. And I hope I've given you the same tools. Thank you.
Thank you, Jerry. Thanks a lot for coming forward.